Evening and welcome back, everyone. I am your host, Kev Baker, and you guessed it, it's time for the first Kev Baker Show of the week. And what a cracker I have got lined up for all of you. Hope you've all had a lovely weekend. Hope you all enjoyed Freaky Friday. I had to take the last hour off Freaky Friday. It was just getting far too late for me, and I just had to kind of retire. But I understand it was a brilliant show. And I know all of you out there were tuned in and you all enjoyed it as well. But I'll be back on Freaky Friday this week. Don't panic. And coming up this week, before we get to tonight's very special guest, I'm really excited about this one, folks. But on Wednesday night, we're going to be joined by Dr. Richard Alan Miller. Now, some of you will remember our previous shows with Dr. Miller, and he is one of the characters that worked behind the scenes on the X-Files. He was a consultant to the producers of that show because he literally worked on some of the secret kind of stuff that we've seen in the X-Files. So please, please, please come along for that one on Wednesday night. That's Dr. Richard Alan Miller. And tonight, I've got a very special and a new guest for us all to sit back, listen to, and enjoy. And I must admit, this is going to be a very much a guilty pleasure for me because we all know how I like to geek out. I love the science. Out of all these topics I cover, we all know that space is something that is very much always in my head and in my heart. So with that said, let me introduce to you tonight's guest. And his name is the soon-to-be doctor, and we'll find out more about that in a minute, Brendan Drachler. And he is an astrophysicist, or an astrophysics PhD student at the moment at the Rochester Institute of Technology, working to understand how we can detect the most dense and energetic objects in our universe, black holes and neutron stars. Yes, we spoke about the black holes on here many's a time, and tonight we're going to get Brendan's take on all of this and much more. Now, he's also working to understand the fundamental structure of black holes and how we can learn more about them. Brendan has spoken on topics ranging from our own solar system to the nature of dark energy, to supernova, and many things in between. Now, more information about Brendan and his outreach efforts can be found at, and I urge you all to check this out, folks. I've been listening to a few of Brendan's podcasts. You can find them over at thestateoftheuniverse.com. And that is where you can listen and subscribe to the podcast. And he's also got a YouTube channel. So I urge all of you during the first break or whenever you get a chance, head on over, check out Brendan Drachler on YouTube. So with all of that said, let's get right into this. And Brendan, I've been really looking forward to getting you on the show, sir. Welcome to the Kev Baker Show.
Thanks for having me, Kev. I got to say, I imagine you have a big following in Scotland, in your homeland. You Scottish people are the nicest goddamn people I've ever met. You're so nice. Everything from our pre-show talk to the email exchanges, like the way that you structure your sentences, you make me feel like you're literally my brother. I got to be honest with you, Kev. I'm impressed by how cordial you are. This is not normal for Americans. We are rude to each other over here, and I just got to say, what a warm welcome, man.
Well, I must admit that is really, really kind of you to say that. And I think us Scots, we travel well around the world. We're well received everywhere, and we just like to treat other people the way we would like to be treated, Brendan. It is not too much to ask. It doesn't cost any money. And imagine the world if we all went about it this way. I think things would be healed overnight. But you, like me, you're a very, very nice guy, very approachable, very down to earth, very friendly, and highly knowledgeable. Let me just say that. I've been listening to a lot of your material. I've been really, really impressed listening to you. You know your stuff. And like I said in your introduction there, soon to be doctor, because I know you're a few years away from it yet, Brendan, but you are definitely going to come out the other side of this PhD. And I'm thinking to myself, maybe I've got maybe a future Brian Cox, maybe a future Bill Nye on my hands here. I can look back on this day and say, look, I had this guy on when he was still studying. So I'm really, really excited to have you here, man.
Oh, don't downgrade me like that, man. I'm going to be so much bigger than those guys. What are you talking about?
Good stuff. Now, let me jump right into it, because black holes, this is something that I have spoke about ad nauseum on the show before. And I know it's something that you really are working very, very hard to understand and to explain and to help others out there observe what these things are. I say observe very loosely, because they're one of the few things in this universe that we can't directly observe. And I heard you saying something really interesting today. It was, when it comes to black holes, it's one of the few things that we can only observe from the outside.
Mm-hmm.
And the universe itself is one of the only few things that we can observe from the inside. Could you start us off there?
Yeah, that was that kind of came to me recently when I was thinking. I spend way too much of my time probably thinking about this stuff, but black holes, fundamentally, the only way that we can study them is by looking at them objectively from the outside. We can't explore what's going on in them. And stars are a bit different, right? And even like the most dense stars, like neutron stars, we can begin to understand what's going on in the center, in the core, in the outer layers of these objects. But black holes are not the same. There's a barrier. There's a so-called event horizon. And once you cross the event horizon, you're, for all intents and purposes, in terms of someone looking at you, you're gone. There's no communication. Communication has to cease. There's no way out. So your science, you have to sort of probe these objects in a very interesting way. You have to study them purely from the outside. You cannot begin to question what's going on in the internal components, because that's a question you might never be able to answer. And the universe, and you had Brian Keating on the show, is sort of very much the opposite. We're inside of it. And the best we can ever do is study the event horizon, if you will, which is the beginning of the universe, from one side. We can't look at it from the other side. Maybe we could, put very advanced models into computers and see, these different cosmological principles and how the universe can unfold. But in reality, the only physical observation we can make is from the inside. And with a black hole, the only physical observations we can make are from the outside. And that's just an interesting parallel. And it leads to all sorts of questions like, is the universe itself the inside of a supermassive black hole in some other universe? All these sorts of weird questions that you start throwing around your brain that, frankly, we have no capacity to answer right now.
Absolutely. And, when it comes to black holes, unfortunately, we lost Dr. Stephen Hawking not too long ago, and he was infamous for his talk on black holes, but he wasn't the first person to come up with the idea of black holes, was he?
No, the black hole idea, very interestingly, let's take a trip, if you will, back to the year 1784. This is incredible that the idea of a black hole was being pondered all the way back in 1784. But it wasn't a black hole in the way we talk about them today. It was very different. It was what they were called, astronomers at the time were calling a dark star. And so I need you and your viewers to sort of put yourself on the Earth, which you all are. If you have a ball, right? Imagine you throw the ball up in the air, Kev. What happens to the ball?
You throw it up and it eventually comes back down. It's
going to come back down, right? Unless, of course, you can throw a really fast ball, but you can't. So most humans, you throw a ball up, even if you throw it as hard as you can, it's just going to come back down. Now, what if you were standing on the sun? Imagine we had some spacesuit where we could stand on the sun. And the sun is so much more massive than the Earth. What happens if we throw a ball up in the air now? With the same speed, we don't give it any extra oomph. We throw it with the exact same speed we did here on the Earth. What's going to happen to that ball?
Come back down quicker.
It's going to come back down. It's going to come back down quicker. It's not going to go as high in the air, right? Why is that? Well, fundamentally, if the way we understand gravity, that ball will not go as high because the sun is much more massive, okay? It requires more energy to escape the sun than it does the Earth. Now, imagine that ball you're throwing, Kev, it's not a ball at all. It's not some physical object, but it's a photon, a single unit of light, a tiny little subatomic particle that weighs nothing. Imagine you could grab it in your hand and you could throw it up. Well, if you throw it up off of the Earth, it's going to leave because the speed of light is well beyond the escape velocity of the Earth. You know, when we launch rockets, they aren't traveling at the speed of light and they can leave the Earth. So what about on the sun? If you throw a photon up in the air on the sun, well, obviously it's going to leave because we can see the sun, right? The sun is emitting photons. That's how we see it. It shoots off these little balls. You could imagine a bunch of little people standing on the sun just throwing photons in the air. And that's how it shines. And it takes about 8 minutes for that light to travel from the surface of the sun out here to the Earth where we can actually see it. That's actually something very interesting. If the sun were to blow up right now, we wouldn't know for about 8 minutes. But that's besides the point.
I think that's fascinating.
That boggles my mind. And we can talk about sort of conception of time. But now imagine you're on some object. Okay, you're just standing there and you have a photon in your hand. And you throw it up in the air and you look up and it's going up, 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 up. And then you see it stop and it comes back down. You'd be like, that's very odd. What kind of object am I standing on? Well, the object you're standing on is what was hypothesized back in 1784 as a dark star. A star that is so massive, so dense, that even though it emits photons, even though can be people on the surface throwing these subatomic particles in the air, they will reach a point and they will fall back to the ground. Therefore, no light would be able to escape such a hypothetical object. Now, keep in mind, Kev, this is 1784, and the equations that were derived by John Michel all the way back in 1784 are the same equations that we're able to derive out of general relativity today. Now, that's kind of amazing. It really is an interesting parallel because you have Newtonian mechanics. Some right now you'd think of what is primitive physics, and it's able to make the same prediction that general relativity is just by using some clever tricks in the mind.
Absolutely fascinating. Now, I have to say to you, because my audience will know that for some time I have looked at something called the electric universe model. Now, gravity, as we know, compared to electromagnetism, it's actually a very, very weak force. Now, I'm not sure if you've looked at the electric model of the universe, and I'm certainly not here to debate you or anything like that, Brendan. It's nothing like that. But would you be open to the fact that maybe gravity isn't the main game in town? Or from what you've seen, because I know you work on models and everything else, would you say that the electric model, although interesting, doesn't quite explain everything? Where would you come to on that?
I would say I'm vaguely familiar with the electric universe. I knew it's a sort of an amalgamation of ideas that come out of plasma cosmology,
yes.
Right? Which was put out by Nobel laureate Alfvén. Is that his name? That sounds right.
I think so, yeah.
Yeah, all the way back in like the 1970s or something. And this Nobel laureate actually is a reputable person. He's a reputable scientist. Naturally, he won the Nobel Prize. But some of the things that he developed, these Alfvén waves, which is what he ended up sort of winning the Nobel for, pioneering magnetohydrodynamics as we know it. Magnetohydrodynamics is a fancy way of saying how fluids move in magnetic fields. It's something I'm work with all the time. Magnetohydrodynamics is an incredibly important field if we intend to study anything in the universe. But he put out this idea of sort of plasma cosmology. And I'll say this, the electromagnetic force and the gravitational force, it's hard to compare strengths because they operate in different regimes, okay? The reason that inside of the nucleus of an atom, the reason that gravity does not play a negligible role is because the mass of the particles is so small.
Yeah.
The mass of the particle is so incredibly tiny. But on large scales, like the size of a planet, look at the Earth, for example. We know that the Earth has essentially a net neutral charge. Okay? In fact, the reason that we sort of know that is because we know that the ground is slightly negatively charged. The clouds are slightly positively charged. That's why we have lightning. Yeah. We have these two charges sort of trying to equilibrate with one another. But on scales the size of planets that don't have noticeable charge, gravity dominates because the masses are so big. I would say that there's two things going on here. Number one, on those subatomic scales, you don't see much gravitational interaction because the charge dominates over the mass. And on large scales, you see gravity dominate because the mass dominates over the charge. Now, I know that these theories, these ideas are put out there. They try to explain all sorts of things. And I haven't looked into many of the postulates, if you will, about the electric universe. But as a scientist, I'm always inclined. You have to be inclined to new ways of thinking. You have to be. It's imperative. That's how we build our careers, by proving each other wrong. There's
encouraging to hear you say that. And I say that because very, very often people like myself and alternative media, I use air quotes there, we tend to think that all science, basically, if scientists want to get their funding, they basically have to go along with the given party line. And there is no challenging the kind of given facts that are out there. So to hear somebody like yourself saying that you have to keep an open mind and you have to keep going back and retesting and challenging these theories that are out there, I find that really refreshing. It's also something I said to Brian Keating as well, because I've been guilty of it, Brendan. I've been guilty of saying when it comes to climate change, often I've said, well, these scientists will never tell us the truth because they want to get their funding. However, listening to you saying this, it gives me a totally different perspective on that.
I actually think this is a systemic problem that has not so much to do with funding. Here's what I think the problem is. I think the people who tend to get the funding, the large projects funded, are people who are very senior in their careers. And also the people less likely to develop really revolutionary ideas are senior in their career. So I think that there are two different issues there. The fact that people who've been in a career for a long time, let's take, for example, trying to discover dark matter, okay? People who have worked their whole career trying to discover dark matter, and they come up with all these ideas. They're like, okay, we think that dark matter is composed of WIMPs, weakly interacting massive particles. So we'll develop some experiment that should be able to detect two WIMPs colliding into one another in the outskirts of the galaxy, and they will pour their career into it, 40 years. And then they want to get this massive experiment funded. And let's say they go ahead and they get it funded. They get this $40 million project funded, this huge, I don't know, whatever an experiment would look like that would try to detect dark matter. We don't really have many of them right now, so it could be something revolutionary. The people that are going to be able to get those funding are the people that are very senior in their career. And they're the same people that are so set in the idea that dark matter exists because they built a career on it. It's really hard to give up the idea that something is fake, that you're wrong, that your life's work was for nothing. It's hard to do that. And in science, sometimes you have to do it. Now, I'm not saying dark matter is not real.
No,
I want to make that perfectly clear. I'm just using it as an example, as someone who because as of yet, we have yet to detect it. But there have been people working tirelessly on trying to find it for their whole careers. But I think that young scientists have revolutionary ideas all the time, but they don't have the means to get those revolutionary ideas funded. So they end up working underneath people who want to work on the same idea for many, many years without progress. Now, that's not to say nothing gets done, right? We naturally get a bunch done. I don't want to give you the idea that scientists aren't doing anything. We're absolutely doing stuff. But the way that funding is sort of given to people with seniority really holds back new ideas from forming. But, Kev, I got to say, there's a good reason for that at the same time, on the flip side of the coin. Because if we started giving money to every new idea, well, there would be really dumb ideas being funded. There'd be people trying to fly, spacecraft up into low Earth orbit to see the curvature of the Earth because they think it's flat. So there's a reason that we sort of treat it this way. We need to make you prove yourself as a scientist, then you get money, as opposed to give you money, try to prove yourself as a scientist. Does that make sense?
It makes absolutely perfect sense, my friend. And, we've kind of gone all over the place here so far, and I'll take the blame for that one. This is the way the Kev Baker Show goes. But you mentioned something very topical there. And before we go to the first break, we've got about 5 minutes or so left. I know you wanted to touch on this, and it was the flat Earth issue. Now, I was saying to you before the show, I really don't know where it came out of, and you had a theory as to why it took off, and I'd like you to get that across to the audience.
Yeah, I think the Flat Earth Society, if you will, has been in existence for a long time, right? But I think what really set it over the edge, what really made it a popular, and I don't even like using the word popular because I don't like to give it credence, because I don't think it's popular. I think it's a very vocal minority that is on Twitter, on Instagram, on Facebook, on social media. And I think what really made the ranks increase is, first thing is that we had popular figures really taking hold. You had people, athletes, you have, rappers, etc. in America saying, I believe the flat earth. And they have a large following of young, susceptible people. And I think the same way that you can get LeBron James to sell Nikes for you, the same way that you can get, Tom Brady to sell Gucci for you, you can get young, susceptible kids to buy into scientific theories that are frankly not theories at all. They're nonsense. But because they don't have the capacity to really think for themselves, because in that age group, you really are just sort of taking whatever the people around you are willing to give. You're eating it all up. You've been trained to do that. That's what school does to you. It says that you should sit in a classroom and you should just sort of consume the material being thrown at you. And then when you have someone you look up to throwing material at you, and that material is just unscientific, unfortunately, you don't have the capacity to say, wait, you're stupid, you're wrong. Instead, you just consume it and you let it sit in your brain, and it's a real problem.
No, I can imagine it must be quite frustrating for somebody like yourself, but I also imagine it's not something you waste too much time on, right?
No, in terms of real life, I never, ever have encountered anyone who believes that the earth is flat. Never. And I've done planetarium shows throughout my young career to, over the course of the years I've been doing shows, thousands of people. And never one time, people come up to me and ask me all sorts of crazy stuff. And I forgive them each time because, I don't want to shame anyone. But no one has ever come up to me and said, Brendan, the earth is flat. Here's why. That has never happened. I do think it's like a small minority on the internet that really latches onto this.
Well, before I got into this, I was in the military and we done satellite communications. So obviously it never ever really sat well with me when it first kind of exploded onto the internet. I respect anyone for their own beliefs, and I certainly would be open to speak to people who believe the earth is flat. However, it's just hard for me to even wrap my head around, Brendan. It really is, because of everything I've been taught in the past. And that doesn't make me better than anyone else. It's just kind of the mindset I come from.
Yeah, it's a very interesting. I was on the Flat Earth Society webpage earlier today, actually, in preparation for this. I was trying to look into the extent of their organization, and their organization seems quite large. It's very interesting. And here's what I say to those people that believe in this flat Earth. I say, here's what you do: you set up a GoFundMe, you set up an online webpage to donate money, and you start yourself a space program, and you launch yourself into low Earth orbit, and you see for yourself. You don't have to have the government involved. You don't have NASA involved. Just go ahead and do it. Launch yourself into low Earth orbit. If they won't let you do it in America, go to China, go to India. I don't care. And tell us, is the Earth round or is the Earth flat? That's it. Test your theory.
Absolutely, brother. And of course, for anyone out there listening who may be a flat earther, we do have shows on the network that cover that stuff. And I'm sure by now, it's not my thing. And I'm glad we've got shows that cover that, because that means I really don't need to tackle that issue. And we've got so much more on the other side to come back and get into. We're going to get into more of the black holes, because Brendan here, he's working on some modeling, simulation stuff that may actually help astronomers out there detect things around the black holes. We're also going to get into something we've spoke about before, very interesting, fast radio bursts, and so much more. Please remember to visit Brendan's website over at thestateoftheuniverse.com, and also I will drop a link to his YouTube in the chat during the break. Don't go anywhere, folks. We will be right back.
This is the Kev Baker Show.
Welcome back, ladies and gentlemen. And you are lucky to have myself and Brendan Drachler here back tonight, because I could pick this guy's brain all night long. Brendan is an astrophysics PhD at the University of Rochester. He's currently studying there. We were talking about black holes. We're going to get into fast radio bursts, but really, I was quite rude during that first segment, Brendan, and I'm sure you've got a lot more or something else you could add on the whole black hole thing before we get to these very interesting, very intriguing, and very topical fast radio bursts. So is there anything else about the black holes that you would really like the audience to kind of consider, to think about?
Yeah, first, real quick, Kev, I will correct you so that my fellow colleagues don't get upset. I am a PhD student at the Rochester Institute of Technology.
Okay.
The University of Rochester is like a rival school, 20 minutes down the road. So I don't want to give anyone the impression that I'm two-timing them over there at
Absolutely.
Rochester.
I apologize for that, brother.
No issue.
So
I think we sort of.
You've got a black hole in the middle of our galaxy, right? The Milky Way.
Yes.
Now, why is it then that the entire Milky Way doesn't slowly get gobbled up into this black hole? Or will that eventually happen over time?
Yeah, this is a question that seems to pervade science fiction, I think. I haven't watched the movie Interstellar, but I think it's about flying into a black hole or something. I really should get around to watching it. It's like 4 years old now.
That, man. You'd like it, I think.
Yeah, and so will the black hole swallow the galaxy? No, it won't. And so let's go back to our solar system. If tomorrow the sun underwent some miraculous process that is not physical, but let's just pretend, okay? A lot of times when you have to explain astronomy to people, you have to make up all these weird scenarios. Let's pretend that the sun turned into a black hole tomorrow. It weighed the same. It was the same size, everything. It was just sitting there where the sun is now. What would happen to us? Absolutely nothing. The only thing that would happen is that we would stop getting sunlight beating down on the earth. The place would get very, very cold. We would all die for sure, but we wouldn't die because we got sucked into the black hole. Because Newton, the laws of Newton put forward some, 400 years ago, and then the laws of Kepler tell us that the black hole is not just going to suck in the earth, because frankly the earth doesn't care what is in the place of the sun. It only cares how massive it is. That's it. The black hole is not just going to mercilessly suck all the planets in. They will still rotate like normal, which is why in the center of our galaxy we have that supermassive black hole. It's like 4 times 10 to the 6th times the mass of our sun. So about 4 million times the mass of our sun. You could pack 4 million suns into this black hole, which is, by all accounts, a lot, okay? And that is actually on the lower end of supermassive black holes. We detect black holes with many, many more solar masses in them. Billions, hundreds of billions, trillions even. So these things get really, really big. But they don't just mercilessly suck everything in. Things just orbit around them like normal. In fact, the way that we know that there's a black hole at the center of our galaxy is because they don't suck everything in. Because we can observe a star. The star's name is S2, okay? And we observe the star. We can observe it as it goes about its business. We observe it over decades, okay? And we can see that it's orbiting something very close to the galactic center. We don't know what it is. We can't see what it is, but we can track the motion of this star, S2, through the sky. And we can track it with our best telescopes, and we see that it goes in an ellipse, just like an orbit would. And when something goes in an ellipse, when we can track its period, how long does it take to orbit around that object? How large is the orbit? We can use all of these parameters to understand how heavy is the object that it's orbiting. And by doing that, by tracking the movement of this star S2, we are able to determine that whatever it's orbiting around, we can't see it, but it has to weigh about 4 million times the mass of our sun.
Now, would that be similar then, Brendan, when they're looking for and identifying exoplanets transiting around a foreign star? Is that how they are able to work out kind of their density, their size, whether they're rocky, gaseous? Are they watching the same kind of elliptical kind of journey?
There's some subtleties in the way we do exoplanets compared to this in particular, because a lot of the ways that we do exoplanet research is we use the so-called transit method, which you mentioned. We look out there.
I think it dims the light from the star that you're looking at, doesn't it?
Right. Yeah. If you move your hand, if you have someone standing off in a field, some 20 yards away from you or 20 meters away from you, and there's a light bulb out there, and they're putting their hand in front of the light bulb over and over again, you might be able to detect that the light is dimming in that light bulb. And exoplanet research is very much the same. We look at these stars far, far away, and the dimming effect oftentimes can't even be noted with the naked eye. If you're looking through a telescope and you're looking at the images, sometimes you can't even see it. It is very clever algorithms that can detect these very subtle dips in light when a planet goes in front of its parent star. And there has to be really special features, really special circumstances for us to determine, is it a rocky planet? Is it a gassy planet? Things like that. A lot of it comes down to how much light was dimmed. Was the planet big? Was the planet small? And we sort of answer some of these questions. Some of the planets closer to us, like in the Alpha Centauri system, the star next door, we began to detect exoplanets around that star, which is amazing because that means that within our lifetime, we might be able to witness, Kev, us sending out some form of nanobot. It's got to be small so it can travel very fast.
Is that not only 4 light years away, Brendan?
Yes, it's in terms of astronomical terms, it's really close.
That's like just a hop and a skip away in astronomical terms.
Yes, and so to answer the question at hand was, is this the sort of way that we detect and learn about exoplanets? I would say it's very different, because in this case, the only thing we can infer from the orbit of the star S2 is that it's orbiting around something 4 million times the mass of our sun. That's it. In the case of exoplanets, we can often infer some other stuff. We can infer things like you mentioned, densities. How big is the planet? Is it gaseous? Is it rocky? Is it orbiting in the habitable zone? Things like that. And I don't do a lot of research in exoplanets, but I've sort of spoken about some of these things in the past. And so I hope that addresses the question you had.
No, absolutely. And again, I apologize because I get so excited when I've got somebody like you on the show here. I could just literally pick your brain apart. But let's move on then to the fast radio bursts, because this is something I've had a lot of fun speculating about and theorizing about on the show. Could it be aliens trying to make contact? That's the more far out kind of theory we've come up with. But what's your take on these things called fast radio bursts?
Yeah, I would like to actually address something real quick, and it's in relation to this. Absolutely. And it's pulsars. Back in 1967, Jocelyn Bell Burnell discovered the first pulsar by accident. She was looking at radio data from a radio telescope. This is back in the day when it wasn't digitized. It wasn't on a computer. They would print out these long strip charts. If you ever seen the old movies at the time, and you were in the military, so maybe you saw something like this. You would have a pen that traced over papers. Yeah. And it sort of, drew out a little picture for you about intensity. How bright is the thing you're looking at? Yep. And Jocelyn Bell would study these strip charts, and she noticed something very interesting. She noticed that there was a signal, and it appeared to be repeating at an incredibly precise interval. Now, when she discovered this, there was a lot of speculation about what this thing could be. In fact, this is an interesting tidbit. They jokingly named the first pulsar LGM-1. Do you know what LGM stood for, Kev?
I do not. No.
It stood for Little Green Men 1. They jokingly named the source that because there was actually a lot of belief that, oh my God, nature could not create something so precise. This has to be intelligent life trying to contact us. Turns out it wasn't. It was a neutron star spinning with incredible regularity, and now we can detect them all over the place. They're very plentiful. We're able to find hundreds of them. Now, back to fast radio bursts. They're very interesting. They're an anomaly that was discovered in much the same way by Duncan Lorimer back in 2007. He was looking at old radio data, and he noticed something. Actually, I think it was an undergraduate student of his that first it caught his eye. And then he said, advisor, Dr. Lorimer, what is going on here? And they sort of explored it more. Now, if you're interested, a shameless plug here, I had Duncan Lorimer, the discoverer of these FRBs, on episode 15 of my show that I encourage anyone interested to go listen to. We talk about what it's like to make such a monumental discovery.
That's my time listening taken care of tonight then, Brendan. Thank you.
Oh, you're welcome. And so, he discovers these objects, and at the time we only had one. In fact, it got the name the Lorimer Burst, named after him at first. And then we started to find more. And then we started to find more. And then, I think it was last year, although it might be 2 years ago now that we're in 2019, we discovered the first repeating fast radio burst. A fast radio burst that doesn't just blip once and turn off, because that's what all the FRBs did that we found to date. They don't repeat like pulsars. They go blip and then no more. Shut off. It happens so quick that you can't even localize it. You can't localize it well. You have zero precision. You know the general area it came from in the sky because you had a telescope pointed there, but you can't localize it enough to look at it with an optical telescope or look at it with an infrared telescope. You're left in the dark. Now we have these repeating FRBs that started to pop up. And then late last year, I think it was late summer, the Chime radio telescope came online as a testing phase. And that's a Canadian radio telescope. And it detected 13 new FRBs in a real quick time. And when it's fully operational, they expect to be able to detect hundreds or thousands of FRBs. And then we can start to answer these questions, Kev, like what are these things? Because we'll be able to start to localize them. We'll be able to say, whoa, there was a fast radio burst. I know right where it came from. Now I can point our most powerful telescopes in that region and see if I can find something interesting. Because it's got to be something that's rare. Another thing that's interesting about these FRBs, Kev, is that they tend to be extragalactic in their origin. Now, we don't know that for sure, but we're fairly certain they're not coming from within our own galaxy. They're coming from the intergalactic space. Not the intergalactic space. Sorry, that implies that they're coming from in between galaxies, which is not the case.
Yeah,
they're coming from
the next galaxy or another galaxy.
Yeah, galaxies far away. And the reason that we know that is because radio waves, which is where the fast radio burst comes from, is that the fact that these emissions occur in the radio. They tend to do something interesting when they travel through space. They get what's called dispersed, which means the frequency gets shifted. Now we can detect by the amount of shifted frequency, how far is the frequency shifted, we can begin to understand through how much space did this radio wave travel. And they are shifted to the point where we believe that they're coming from another galaxy.
That is amazing. It truly, truly is. Now, to put you on the spot, and there's no way we could ever tell, but do you think this is a new kind of object in astronomy? Or would you be open to the fact that this could be some kind of intelligent signal?
I think, now I should say, I am by no means an alien denier. We can talk about aliens in a few moments if you'd like, but I don't think this is them.
After the break, for sure, yes. I don't think so, no.
No, and the reason I say that is because we're detecting these fast radio bursts all over the sky in different regions, okay? Now, maybe if we only detected one fast radio burst from one area in the sky, and it sort of repeated, or it doesn't even have to. What if it just blipped one time, and there was only one of them? So back in 2007, when Duncan Lorimer discovered the Lorimer burst, the first one, I certainly would have been on board. I'd have been like, wow, maybe that is aliens. But the fact that we can detect similar signals from all over the sky indicates to me that there's probably something fundamentally natural happening. Because I wouldn't expect all intelligent life, if it was scattered over here and over there and in the south and in the north and above the earth and below the earth, I wouldn't expect it to had somehow come up with the exact same way to emit the similar signals. I wouldn't have expected that.
It's a really, really logical way of thinking about that. It really is. I like that idea. And how much then? We know a heck of a lot, or we think we know a heck of a lot about the universe. How many other things out there do you think are still to be discovered? I know it's hard to kind of describe that because it's things we haven't found yet. But I mean, maybe we don't have the instruments. Maybe we're not looking for the type of signals that are coming into us, not from aliens per se, but astronomical features like we mentioned the pulsars, maybe some form of new dense planets, black holes, white holes, something else that we haven't thought of yet. Do you think there's still a lot that we need to learn?
Oh, there is so much. And one of the interesting things, the thing that I find very, very, very cool, and I think any young physicist, maybe a kid in school, in high school still, who wants to become an astronomer or physicist one day, you should look at this and be motivated the same way I was. The fact is, and I talked to Duncan Lorimer about this when I had him on my show, is that there's probably data sitting around right now in some archive somewhere, whether it's radio telescope data, whether it's pictures that were taken with optical telescopes like Hubble, whether it's infrared data, whatever it is, X-ray, etc. There's probably data sitting around right now that has an incredible achievement just waiting to be found inside of that data.
Spot on. I've said for some time, I often warn about the advances in artificial intelligence. However, when you deploy a specific AI, say at somewhere like SETI, it could pour through all of that data that's coming in constantly, and it can find patterns and things that we weren't even looking for in the first place. And like you say, all of the data that already exists out there, you employ an AI on that, and who knows what's already sitting there waiting to be found.
You're absolutely right. And that's being done in a lot of labs across the world, where these labs are beginning to realize, what would really help if we had a computer sorting through all this, and they can sort through it, and they can sort through it fast. A lot of times it just comes down to the limitation of the computer itself. It can only go so fast because some of these labs, they have hundreds of terabytes of data sitting around, Kev, on these large clusters, and they have no one to analyze it. And you can have a computer sit down, and they don't have to sit, and you can have it sit anywhere. You can have the computer sort through all the data, but it's going to take a real long time because the fact is we will always be able to collect data faster than we will be able to look through it. And that's true of anything.
And with the advances in technology and the new telescopes that are going up, I believe there's one called, is it the Webb telescope? I mean, the data just keeps on increasing. And it's almost impossible for humans to physically pore over that.
Yeah. The James Webb Space Telescope is going to be going up, and that is an incredible project. It really is a fundamentally interesting project.
I can tell the look on your face that you're excited about that, dude.
Yeah, well, I would say I'm more excited about the deployment of the instrument itself than I am about the instrument. Because I'm not sure how much you're familiar with this instrument, but it's going to be pretty big, right? It's going to be huge. It's got to be in order to collect the sorts of data we're trying to collect. And we are shooting it away from the Earth. We're shooting it away from the Earth into a stable point on the Earth's orbit, what we call a Lagrange point. And ideally, as it sits there, it won't be moving. It will just follow the Earth as the Earth orbits. It's very, very far away from the Earth, so it won't be getting any signals. Some of the problem with telescopes that we have on Earth is that they pick up the signals that we put off. This is especially true for radio telescopes because we drive our car and we listen to the FM stereo. I don't know, Kev, is this being broadcast over radio right now?
Yes, it will be, yes.
Yeah, so even this broadcast will cause interference in radio telescopes in the general region that it's being broadcast in.
See, that's one of the kind of issues I have with the LIGO experiment that's trying to detect the gravitational waves. I mean, literally a butterfly going by that thing could set off some of the sensors in there. So it must be terribly difficult for them to differentiate between a gravitational wave and, like you say, just something else that we've produced.
Yeah, that's an important point, and that's why they built two of them. That's why we have one in Washington, and that's why we have one in Louisiana in the United States. And that's so that if there is a systemic problem, if there is, I remember in the case of the Louisiana LIGO detector, there was people that owned the land next door that were chopping down trees, and they had to send out these engineers to find out what the disturbance was. And they had to say, hey, you got to stop chopping those trees. And I think the government ended up having to give them some money in order to make them, stop logging next door, because the chopping of these trees was causing interference across the way in the LIGO detector. But that's why we built two. We built two so that ideally you wouldn't have something going on in Louisiana impacting the LIGO detector that is also impacting the Washington detector in the same way. And if there was something like that going on, then we probably have a massive earthquake underneath the United States that is a much bigger problem than the fact that our data is going bad.
Absolutely. Now, aside from gravitational waves, I mean, we're flying through space at a tremendous speed, albeit we don't appreciate that, stuck here on terra firma. Now, are there cosmic energies, cosmic waves? Is there any way that the planet could be affected by some particles coming in, some wave of particles, maybe from even the center of our own galaxy as we transverse that? Is there any effect that would have on the planet?
Not in terms of seismology, not in terms of, like physically shaking the planet, unless we were to get hit by, some asteroid or something. But in terms of these subatomic particles, we get blasted with them every day, whether they're coming from the sun, whether they're there's an amazing statistic, and I'm not sure of the exact number, but there's an amazing amount of meteorites that land on our planet every day. It's some thousands of pounds worth of meteorites land on our planet every day. Now, of course, almost all of them are vaporized when they enter the atmosphere. But nevertheless, that amount of mass is being added on every day because the solar system is a messy place. Like you say, Kev, we are hurtling through space, and other stuff is hurtling through space too. And we're thankful that we live in the solar system at a time where there doesn't seem to be a bunch of bombardment. There was a time in the solar system's history where there was a ton of bombardment. There was comets and meteorites and asteroids and all sorts of stuff smacking into all of the terrestrial planets, Mars, Earth, the moon. You can see the remnants of it still preserved on the surface of the moon. All those craters you see, they occurred because at one point this was a violent place. But to answer your question directly, Kev, I don't think that there's anything impacting the Earth that would cause signals to be affected.
Because there is a lot of talk, in alternative media about how these energies perhaps could cause earth changes, increased earth changes. And again, I was just wanting to get your kind of take on that. So I think you basically covered that there.
Yeah, I see. This is the thing. I like to be open to ideas. I do. I like to be open to ideas because this is what I see a lot in a lot of science media, and I actually think that it furthers the problem. I see someone maybe naively propose an idea, and then you have people who call them stupid, who vilify them, who say, no, your idea is dumb, it's stupid. They call them ignorant. They call them, deplorables or whatever they call them. And all that does, Kev, is it makes them want to latch onto their ideas more. And it makes them want to get further and further away from the truth and hold on to those ideas. Because letting go of those ideas means admitting that they're stupid. It means admitting that they're deplorables. It means admitting that they don't know anything. And so no one wants to do that. So they latch on and they hold on. And, they get vilified, but it doesn't matter because they put themselves in a bubble. And they don't allow that bubble to be penetrated anymore because they've shut down. They've shut down new ideas. Because anytime they try to enter into the free exchange of ideas, they get called stupid. And it's a real issue. But I'll admit, sometimes I do want to make fun of people.
That's natural. And, I always tell people, I'd never, ever tell people what to think. I just like the thought of this show encouraging people to think for themselves and to keep that open mind, Brendan. because you have to keep an open mind on everything, because we're just one piece of new information away from anything that we believe being totally thrown up in the air, right?
That is partially true. We have some truth.
Not an open mind to the point where your brain falls out, but but opening up.
Yeah, you have to be open to new ideas. You just have to be. That's how science progresses. That's how anything progresses. You know, what would be the point in having a capitalist society if you suppress new ideas? You need new ideas. It literally pushes the world forward. The problem, though, is that you need to be careful when you freely exchange those ideas. Because if the right person gets a hold of the wrong idea, you can very, very quickly end up in a very bad place. And then his history shows us that.
That's a very good way of putting it. And I can't believe it. 1 hour down already, folks. I hope you're all enjoying this half as much as I am. I dropped the links in the chat room for Brendan's website and his podcast over on YouTube as well. I'll include the link to his YouTube channel in the notes for this video. And I want all you KBS listeners out there, head on over, subscribe, show Brendan some support, because as you can hear here tonight, this is a breath of fresh air. It really, really is. We often talk about the world of science. Well, now we're going to the people at the heart of it. We're number 2 on today's brilliant Kev Baker Show. And yes, it sounds big-headed to say that about a show with your own name on it, but it's nothing to do with me. It is our very special guest, and his name is Brendan Drachler, soon to be PhD, and he is educating us all tonight, or at least he's given us a lot to think about when it comes to the universe. And before we launch back into things, let me just remind all of my listeners out there, and I urge you all, it's mega important that if you want to support the show here, you know I'm sponsored by Get the Tea over at getthetea.com. Well, I was speaking to Ronnie today, and now that Christmas is out of the way and we're all starting to get back on our feet, or some of us are, I urge you all to check it out. And for anyone who doesn't know what Get the Tea is, it is the tea that will change your life, literally. All of these toxins we have inside of us, you can get rid of them with one nice cup of tea, or lots of nice cups of tea. And nothing does what Life Change Tea does. So I urge you all to head on over there. And as a special bonus to the Kev Baker audience, if you are in the United States, if you put in coupon code KBS at the checkout, you will get absolutely free shipping. That is free shipping in the US with coupon code KBS. So with that said, please, please, please head on over there. Not only will you be looking after your own body, but you'll certainly be going a long way to keeping the Kev Baker Show on the air. So then, during the break, we have been joined by Johnny Whistles. And I knew Johnny would be along tonight because myself and John, we both share a passion for these kind of topics: space, exoplanets, fast radio bursts, black holes. And John, I was speaking to you earlier on today, and right behind you on your camera was a big, bold telescope. So this is going to be right up your street, brother.
No, definitely. I was listening to yourself and Brendan there, Kev, talking about these fast radio bursts, and it's weird how they all seem to come in different frequencies. One that turned up, I think it was in August last year, that's got them all perplexed. It came in a frequency that they hadn't seen before. Do you know what I mean? So it's really weird that, I mean, I don't know what they are. I don't know where they're coming from, but I mean, when you get them from something like 3 billion miles away, Kev, do you know what I mean? It just beggars belief.
That's probably 3 billion light years away, which is even more astronomically huge. But now, Brendan, you can see why I call him Johnny Whistles, right?
Yeah. Yeah.
I was trying to explain to Brendan why you have that name, but I thought, well, we'll just let your fast radio burst do the work, Johnny. But Brendan, we were talking briefly before John joined us. I was saying to you how I'd never thought about these fast radio bursts, how you had explained it. Say it was an alien civilization, older, younger, whatever, somewhere out there in the universe. It would be kind of strange to think that you would get that same signal, that same technology perhaps, all over the universe, right?
Yeah, that would definitely be very interesting. And so it would make you come to two conclusions. It would make you either come to the conclusion that these fast radio bursts are some fundamental process going on in nature that we don't fully understand yet, or it could make you come to the conclusion that this alien species emitting this fast radio burst, wherever it is, whatever it is, has the ability to move through space at incredible rates. And every time I've seen this in sci-fi, and every time you see a little blip on the fast radio burst, that's the spaceship sort of firing off, right? You got to wrap your head around how a sci-fi movie could very easily be mimicking this exact same scenario. So I think that the more likely option, and the one I'm inclined to take as an astronomer, is this is a fundamental aspect of nature that we have yet to understand.
Absolutely. Now then, with that said, are you open to the possibility of alien life out there? Either past, maybe it's gone away by now, maybe it's died off, extinction level event, something like that. What's your thoughts on that? I mean, is it just us here in this vast universe?
That is an interesting question to ask, and my answer is that
speculate. I know all we can do is speculate here.
Yeah, and I'm down to speculate all day. My answer is that I don't have it within me to believe that we are the only things in the universe. I can't be that egotistical. Here's the thing, okay? Do you play the lottery, Kev?
I used to.
Okay, I'm a person who plays the lottery, okay? Let's say your chances are 1 in a million, okay? Let's say you buy 2 million tickets. Statistically, should you win the lottery?
Nope.
You should. You should, right?
You should, but...
You should win it twice even.
Yeah.
Statistically, yeah. Now, will you? Probably not, because it's rigged, I think, to steal your money. But
I've got the luck of somebody that has no luck at all, dude.
Yeah, no, me too. I agree. But statistically, you should win twice, okay? If winning the lottery is a 1 in a million chance and you're just plucking tickets at random and you buy 2 million tickets, you should win the big one 2 times. Now, let's imagine that the chances for a planet around a star to have a life form on it is, say, 1 in 300 billion. Okay, let's say that. Now, that's a really small number. That is a really conservative estimate. 1 in 300 billion. One planet per 300 billion planets. Or better yet, we could say one form of life around a star for every 300 billion stars. Well, what would that mean? That would mean in the Milky Way alone, there should be about 1 intelligent life form. But that means in the Andromeda galaxy next door, there should also be 1 intelligent life form. The fact is, Kev, the numbers are too great for me to sit here and say it's not possible. I do not believe that the odds can be any greater, any smaller rather, than 1 in 300 billion. I can't imagine. The space is so vast. Our galaxy is like incomprehensibly vast. There's hundreds of billions of stars in our galaxy alone. And there are billions of galaxies in the observable universe. So, is there life out there? I think without a doubt there is undoubtedly intelligent life somewhere in the universe.
See, I like
beyond the Earth.
I like that. I do like how you went about explaining that, because 1 in 300 billion, it sounds like a long shot at best, but we really struggle to wrap our heads around these numbers and the size of the universe. So when you actually start to explain it with the lottery ticket analogy that you used, I certainly see now, yes, absolutely that. I mean, I'm very open to it. Absolutely open to it. Whether they've been here or not, you could make a case for and against it. But Johnny Whistles, I'm liking this idea. Absolutely. That makes a better case for us the next time we try to argue our point that there may be aliens out there, right?
Yeah, Kev. Do you know what I mean? When you consider the vast expanse of space, do you know what I mean? It's ridiculous to think that we are the only intelligent living species that's out there. Do you know what I mean? Because there's galaxies out there that are a lot older than ours. Do you know what I mean? They're millions of years older than ours. And to think that what might be out there, Kev, is incredible. But the thing is, that's all we're doing just now is thinking what is out there because we haven't found it yet.
Absolutely. And certainly our current means of space travel, Brendan, we won't be going to the Andromeda galaxy anytime too soon, not in our lifetimes. But for me, this is a really exciting time for young guys like yourself, astrophysicists, when you see almost the commercialization of space. You've got Elon Musk with SpaceX, NASA, they've kind of fallen by the wayside. You've got Jeff Bezos with Blue Origin. We've got Richard Branson over here, and there'll be XYZ others that come along. Does this excite you, or does it scare you in some ways? Because what will happen to the solar system, our planets, namely Mars? Hopefully we won't go down the same road as we did on Earth, right?
Yeah, I want to answer this question in two parts. First, I want to address what you said first about traveling to the Andromeda galaxy. This idea of going to different galaxies, to even the other side of our galaxy, it doesn't excite me. And the reason it doesn't excite me is because we will never be able to realize the fruits of our labor in our respective lifetimes.
Exactly.
Because of the way that relativity tells us time dilation works. If we have to travel to the Andromeda galaxy, the only way we're going to get there in a reasonable amount of time is to go really, really fast. A respectable fraction of the speed of light. But time ticks much, much faster here on Earth relative to the person inside that spacecraft. So even though the person in the spacecraft might travel to the Andromeda galaxy and back, and it took them, 28 years in their time frame, guess what? 10 million years have passed here on Earth. We would probably have killed ourselves by then. So it's as if there's a cosmic paradox. The paradox is we want to explore, but we can't because we'll never be able to understand the fruits of the labor that is exploring the galaxy, exploring the universe. Now, in terms of our own solar system, I'm absolutely ecstatic about exploring the galaxy. And I would point any interested listeners to episode 21 of my show, The State of the Universe. And I sit down with a good friend of mine, Nate, and Nate is a physicist in close, I don't want to say affiliation, but he understands what's going on at NASA better than most people. He has he lives in Houston, Texas. He works closely with the Johnson Space Center. And so he talked to me about the growing age, the so-called billionaire space race, the new space race, the space race that is not done by governments, but is done by private industry. And I'm actually really excited. I'm really excited for it. You have Breakthrough Starshot going on. You have Elon Musk and SpaceX. You have Jeff Bezos with Blue Origin. You have Virgin Galactic. You have all of these things. And they're going to set up space tourism. They're going to set up space commerce. They're going to start mining asteroids. And of course, this is going to be over the course of my lifetime. This isn't going to be something we're doing next week. But we're going to start to explore the moon. You saw the recent Chinese mission that went to the moon, I presume, and they were able to grow cotton on the moon inside of a biosphere, which is incredibly cool. Now, of course, I think it died very quickly, but nevertheless, the capability might be there. And so I really am excited. I think there's some problems with it, and I think that we need to be careful how we proceed. We truly do. We have to be careful. Are you familiar with Carl Sagan?
Oh, absolutely, yes.
Okay, Carl Sagan said this amazing thing. He said many amazing things, but one thing that sticks with me is that he said if we begin exploring Mars and we dig into the soil of Mars and we find that there's a bacterium in that soil, just one bacterium, we are obligated as humans to forget about Mars, to not go to Mars. And the reason why is because at one point on the Earth, we were probably just a bacterium. And had someone disturbed our ecosystem, we might never have become the humans we are today. And so it is our moral obligation to say, okay, Life might flourish on this planet. It might not be tomorrow. It might not be for 1,000,000 years. It might not be for 1,000,000,000 years. But it is our moral obligation to say, you know what? There's life that could potentially flourish on this planet. Therefore, we cannot disturb that ecosystem. I think that's a great sentiment. Now, I don't think we need to be that careful, Kev. I think we can responsibly explore our solar system. I don't think we should not do it because there's bacteria in the soil of Mars, although I get the sentiment. But I do think we need to be very careful because we cannot begin treating the entire solar system the way that the billionaires of our planet treat the Earth.
Okay, now, here's something for you. And I want your take on this because there's something called the Van Allen radiation belt. And NASA not long ago said that they still can't figure out how to get astronauts through that, despite the fact that we obviously had the Apollo missions. Now, the Apollo missions, the moon landing, obviously one of the biggest kind of controversies still to this day. My thoughts on it is we went there. However, the footage that we were showing possibly wasn't real. And I say that only because of the PR exercise and the way the world was at that point, Brendan. With the space race with the Russians, it would have been catastrophic if something had gone wrong to Neil Armstrong and Buzz Aldrin. And the PR victory that would have given the Russians at the time, huge. That said, I still do think we went there. But this Van Allen radiation belt, can you explain what that is? And is it such a major factor that people like myself and others make such a fuss about? Because everyone seems to think that NASA lies about everything.
Yeah, I agree with you about the way that you handle the moon landing. I don't agree with the entire sentiment, but I agree with the way that you sort of approach it. I can see certain conspiracy theories blow my mind in the sense that I don't understand what's trying to be covered up. When it comes to the flat Earth, why would people lie to you about the geometry of the Earth? It boggles my mind. I don't get it, right? What good do they have to telling you the Earth is round versus the Earth is flat? Now, when it comes to the moon landing, I can actually wrap my head around why people would think we didn't go there. It was a very important thing at the time that the U.S. gets to the moon, wins the space race against the USSR. That was a fundamentally important thing. I could understand why we would come up with some PR move to pretend that we had completed something that we had not, and to win the space race and ideally establish ourselves as the world power. I get it. It makes sense to me. Okay, the same way that the sort of JFK assassinations, like I can at least wrap my head around a motive, and I think that that's important if you're gonna put any conspiracy theory. Now, in terms of the Van Allen radiation belts, I'm not super knowledgeable on them. I know that they are electrically charged particles that tend to interact with the magnetic field around the Earth. I would like to see the source of NASA saying that we couldn't get through them. That's something that I would like to sort of analyze, because I think maybe what NASA, and again, I didn't see this release, and I'm not super knowledgeable on aerospace and launching things through the Van Allen radiation belt, but I think that maybe they didn't say quite what was interpreted.
No, absolutely. I'm just trying to see when that was actually said. But we can come back to that. We can.
Yeah, if we could get someone to sort of find that source, and then we can talk about it.
Absolutely. And I'm hoping we'll be doing a lot more shows in the future anyway, Brendan, because you've absolutely won me over here tonight. So going back to the moon then, we've got China saying that they want to send astronauts up to it. And I always think, if it comes to deeper space exploration, it's a no-brainer, really, that we need some kind of colony, something on the moon, because then you can take away the cost of launching these rockets of the planet down here. Totally negates that. Do you think that's something we'll see at least starting in our lifetime? A moon colony?
Yeah, I think it's something that we will certainly see starting specific. I should talk about the U.S. quick. The U.S. has a real problem with its space agency because of the way that our presidents tend to handle it. I see a lot of talk about NASA not being very good in terms of its ability to get us places in recent years. And this all comes down to the way that the U.S. presidents have sort of looked at the moon. Back in the era of George Bush wanted to go to the moon. He wanted to focus on the moon. He wanted to get us back to the moon. He wanted to begin colonizing, not literally setting up commerce, but get a reliable transportation method there and back, and then move on to Mars. Barack Obama came along and he said, no, screw the moon. No one wants to go to the moon. Let's go straight to Mars. So you had the entire agency had to redirect their efforts and say, all right, guys, we're not going to the moon anymore. We're going to Mars now, which requires much different technology. Then you had Donald Trump come back into office, and Donald Trump said, screw Mars. Let's go to the moon first. And so you have this agency in this limbo all the time, going back and forth, not being able to sort of make heads and tails of what they're supposed to be doing. What I think, Kev, is that if we can get NASA and the private companies to focus on getting to the moon, and you generate competition there, this billionaire space race is a good thing. If we could get them to actually compete to get commerce on the moon first, I honestly think we will get there, and we will have that place colonized quite well in terms of commerce anyway. Maybe not people living there, but we will absolutely have commerce there, whether it be space tourism, whether it be agriculture, something. We will have it there, I think, within our lifetimes if we can just settle on a goddamn policy. If we could just make up our minds and say, yes, we need to go to the moon, and stop changing our minds. China did that. China set out goals for itself from now until 2050, and it is adhering to those goals. It is putting money into those goals. It is not steering away from the goals. It is not changing its mind. It is doing what it said it would do, and that is why that they're getting to the places that they're getting.
Yeah, because it was just Chang'e 4 was their latest one to the far side of the moon. And
That's
I think
right.
Chang'e 5, I think it's actually due to return samples from the lunar surface back to Earth in the next couple of years. And I've heard talk about, is it helium-3, maybe helium-5 before? Is the moon worth mining? I know it's not a good idea for us to go out there and start mining our own solar system, but do you think that might be the thing that encourages companies to get up there?
Yeah, I think that first we will see tourism. I think that's the first one. And I think that's already happening a little bit. I think we're going to start seeing private companies taking rich upper middle class people to the moon for some fee. I think that's what we'll see first. Then, I'm sorry, can you repeat your question just so I know I'm on the right page here?
Once they find something that's worth mining, once there's some profit for them, do you think that would be the major encouragement for them to do it?
Yeah, I think mining will occur. I think the first mining, the sort of interplanetary mining that we will see, will occur on asteroids first. Yeah.
There's a company, they have Planetary Resources that I've looked at before. They've got the film director James Cameron on the board of directors. You often see them featured on the space kind of documentaries, but they're very keen to start mining asteroids.
Yeah, it's an important thing. It's something that will be done, and it's something that in our lifetime might be commonplace. Right now, we have various missions that can go to these asteroids and then launch themselves back to Earth. If you ever seen these, they look like little spiders. Yeah. They land on the thing, and because the asteroids are so small, they have very little surface gravity, and you can just sort of pop yourself off. If a human was standing on one of these asteroids, they could probably run and jump and then escape the asteroid, which is really interesting, really cool.
Super cool. And why is it when it comes to these asteroids and things, Brendan, why is it usually in the media now we're told maybe the day after one had a near miss? I would think with the technology we have now, surely they've got a good idea, a good handle on where all of these kind of near-Earth objects are, right? But
Yeah, it's
again, they say, well, yesterday we were missed by, 0.3 AU distance from the moon. You're thinking, well, how come we didn't know about this before it came in? Is it just so we don't panic?
in some cases, Kev, we actually do know about it, but we don't publicize it. The media, because there's no reason to publicize it, because we know that the asteroid, because of the fact that we fundamentally understand gravitational interaction, we know that the asteroid moving through interstellar space isn't going to just take a U-turn and smash into our planet. We have, if you look up these things by NASA, if you're willing to trust them, anyone listening, they have these great, and it's probably been done.
Trust me, this audience will not trust NASA, but I'm with you.
It's probably been done by private scientists, not funded by NASA. You can plot the trajectories of all known near-Earth asteroids or near-Earth objects, NEOs as they're called, and you can see that in our lifetime we might have some near misses, some close misses. But there's also, because of the vastness of space, there's a ton that we don't know are out there. We just don't. They're really hard to detect. If you it's like this, Kev. If you go outside in Scotland and you find a nice rock, a black rock, like a piece of coal or something, and you shine a light on it, there's not going to be a ton of light that shines back at you. It's not very reflective. And rocks that float through interstellar space, they aren't very reflective either. And so the only way we detect them is because we can see them moving in our telescopes. The only way we can see them, Kev, is if they emit light that is reflected off of their surface. But if they're made of stuff that isn't very reflective, then they're just floating in interplanetary space, and it's really hard for us to find them until they get too close for comfort.
Absolutely brilliant. We've got one segment to go with Brendan. Join us after the break. Check out his website.
This is the Kev Baker Show.
Welcome back, ladies and gentlemen. Final segment of tonight's Kev Baker Show with our special guest, Brendan Drachler. You can find his work and his podcast over at the website, www.stateoftheuniverse.com. You can also search him out over on YouTube, where you can find his videos as well. And I really do, if you're into all the space stuff like myself and Johnny Whistles here, this is going to be very, very up your street. And I'm proud to say that by the looks of it, Brendan has just about survived the Kev Baker Show Inquisition that I've almost put him through here. The guy will probably need a good rest after he gets off the air. I apologise for taking you all over the universe, Brendan. But
no issue. When you're in the academic field of astrophysics, this sort of conversation is very normal. Physicists, astronomers frequently talk about the things that we're talking about here today. We talk about aliens. Are you familiar with the Drake equation, actually? I'll ask you that.
Yes. Talk to us about that.
Yeah, the Drake equation was something that was spurred up in a conversation just like this. It was, I believe, that it was sort of formalized. The equation is not sound, right? It's not a mathematical proof of any kind. It is an amalgamation of things that, sort of different factors. What are the odds that this happens? What are the odds that this happens? And the answer to the Drake equation gives you a probability of finding intelligent life. Now, with that being said, it was thought of, Kev, in a situation just like the one we're having now. A bunch of astronomers got together in Green Bank, West Virginia, United States, and Green Bank is an incredible place. Green Bank, I've been there a few times. I've been in the room where the Drake equation was first sort of drafted up on the whiteboard, on the chalkboard. They still have the original writing, and they even have a plaque to commemorate it. Down there in a bar in Green Bank, West Virginia, on the premises of what used to be the Green Bank Radio Telescope Laboratory, owned by the federal government. It has since become privately owned and funded because the government sort of didn't want to deal with it anymore. But it is it's amazing. It's an amazing area, and let me tell you, a lot of science gets done this way. A lot of science gets done by people sitting down, being willing to talk about new ideas. Now, the ideas aren't always so controversial as, is the moon landing faked? Are there aliens? Things like that. But that's how problems get solved in physics and in astronomy. Astronomers sit down, astrophysicists sit down, and we talk. And we just talk, and we say, dude, your idea is stupid. Or wait a minute, that's a good idea. We should test that. And you work through this stuff by having a conversation just like this. It's very important. It's no wonder that the world of podcasting has blown up the way it has, because human beings talking, sitting down, exchanging ideas freely is literally the basis by which our society operates the best.
This is the thing that I love about the internet. There's some parts of the internet I hate, like social media, anti-social media, but the fact that I can tune in to Brendan Drachler, I can tune in to X amount of hundreds of other opposing ideas from other podcasts. This is what I like, and it's great to have our own ideas and our own theories, but it's even more important to challenge them and to be open to listening to other people's ideas and theories, because like you say, that's when new things are discovered. That's when you get that eureka moment.
Yeah, that's true. It's necessary that people of opposing ideas sit down. I remember I had Dr. Daryl Treffer on my show, and he was one of the first people I interviewed when I started my show a few months ago. And Dr. Daryl Treffer is this world-renowned neuroscientist, and you can even reach out to him to have him on here if you'd like. He talks about some very controversial ideas. He's an expert on savant syndrome, and that's when you get hit on the head and all of a sudden you can do math really well. It's a well-documented disease. It seems to be related to autism. It can happen suddenly. You can have a car accident and all of a sudden you know how to play the violin, some crazy stuff, okay? And he was talking about how at his old age, he's 81 or something. He's very old. No shame on old people, but he's very old. And you can tell when you listen to him talk. No offense, Dr. Daryl Treffer, if you're out there. And he was talking about some ideas in his own field that he has a tough time sitting down and talking with people. And these are some interesting ideas, like, do we have genetic memory? In other words, do your phobias, Kev, if you're afraid of spiders or something, does that come from the fact that some of your ancestors were killed by a spider bite? Stuff like that, right? And he's willing to sit down and he's willing to entertain these ideas. And he's a very old scientist. He's been in the game a long time. And I want to give your listeners that idea that, listen, we're not all out here trying to shut down every idea that doesn't agree. But what we want out of your ideas, if you're someone who likes to propose alternative theories about the universe, all that we ask is that you come up with a way to test your idea. That's it. That's it. That's fundamental science. You make an observation. You hypothesize what could cause the observation. In your case, it might be that the Earth is flat. It might be that we didn't go to the moon, whatever it is. But come up with a way to test it. That's the important part. The important part isn't just that you believe that something exists or that you believe something's real or that it makes intuitive sense. It matters that you can test the idea and make sure that under scrutiny, it's not false. And frankly, Kev, that's one thing that a lot of conspiracy theorists tend not to be willing to do, because in the face of new evidence, Kev, what I notice is that they create some new reason, some new amendment, if you will, to their idea that says, oh, no, wait, we didn't incorporate that piece of evidence before. And then they changed their theory. They said, no, the theory's different now. Now it takes into account that new piece of evidence. But you can't keep adding to your theory. Your theory, in principle, should be as simple as possible. That's the Occam's razor test, after all. You want a theory that is powerful but simple. And a lot of conspiracy theories lack that.
Absolutely. And, I've been at this a few years now on YouTube as well, and I hold my hands up. I used to be right there. The minute somebody said a conspiracy, I would dive right in, and that's all I would see was this conspiratorial angle. And again, not to make me sound better than anyone else out there, but over time, I've had to evolve. I've had to change the way I look at things. And a lot of things that I used to think were big conspiracies, maybe not so much conspiratorial at all. And a lot of the time now, I'm coming round to the more logical, and like you say, Occam's razor, the most logical explanation. Now, that's not to say there aren't conspiracies in the world, because obviously there is. Always people are going to meet and try and kind of put lies out there to further their own agendas. That's a no-brainer. But I absolutely get where you're coming from there. And sometimes, you know, the hardest thing for anyone to say is I was wrong. And
that's absolutely right.
And instead of saying that, it's almost as like you say, they double down, they look for a new angle, and they keep going. And Johnny, I know you want to jump in here too, right?
Yeah, Kev, it was just, Brendan, you were talking about ideas. It got me thinking about, seems that everyone has some sort of think tank. I'm wondering, does the space community have any sort of think tank?
What do you mean by a think tank?
I think that would probably relate to when you were saying scientists getting together and sharing ideas, stuff like that.
I mean, that happens on I would say both local and non-local scales. And what I mean by that is this: every week we sit down with each other at our own university or in our own area. Okay, in my case, it's the Rochester area, New York. Mm-hmm. And we sit down, whether it be at a colloquium where someone's discussing a topic. I was at a colloquium today where someone was talking about the regions around black holes and around young stars called accretion disks. And they gave their presentation, they showed their work, and then there was a question period where we say, okay, have you thought about this? Have you thought about this? Maybe this could be wrong. Why did you make this assumption? And it can get sometimes quite serious, the way that we sort of grill each other, because what we want is to ensure that everyone is not just making ad hoc assumptions. We want to get physics right. And in order to get physics right, we need to have those types of think tanks where we say, why did you make that assumption? Explain it. Is it physically relevant? So we have those local ones where we sit down with the people we know and the people we associate with, and we talk about the projects we're working on, and we all sort of intimately know each other. But it also happens on scales like at conferences, which every astrophysicist goes to conferences every year. They go there, they give a talk, they present their work, they say, this is what I've been doing for the past year. And then people in the audience whom you don't know, in some cases, whom might think your work is wrong. They might think you're doing what you're doing incorrectly, that their way is better, et cetera, et cetera. And you sit there and you verbally jab back and forth. You don't, call each other dumbasses or whatever, but you sort of say, maybe you should try this way. No, this way is better. And there's constantly an exchange of ideas. That's the thing. I said that at the beginning of the show. This is the fundamental misunderstanding about science, I think. The thing is, we make careers on proving other people wrong. We don't make careers on upholding some idea. Einstein didn't become the greatest physicist to ever live because he upheld the ideas that existed before him. Mm-hmm. Newton didn't become one of the greatest to ever do it because he upheld the ideas before him. It is important that you challenge ideas and you be revolutionary. That is how we got to where we are. We need that. We need to have think tanks and say, no, you are wrong. It is this way instead. And then do you know what the difference between what we do and what people who just sit around and talk and then don't do anything is we go out there and we put our idea to the test. We say, okay, I have an idea about how I can test this theory. Now I'm going to put in 3 years of work and I'm going to see if my test upholds. And if your test upholds, guess what? You've got yourself reputable science. You've made a name for yourself. You can now tell other people that they're wrong. You could say, my idea was right the whole time and you were wrong. You were set in your ways. You didn't believe me, whatever. That's how we make careers. That's what we do. Mm-hmm. We say the current status quo is incorrect and here is how. And not only do we say here is how, but we say, and here's the test to prove it. And that's what's important.
And Brendan, that kind of ties in with the work you're doing right now, really, because you were explaining to me before the show you're working on computational models and simulations, and this is going to go a long way to helping astronomers out there observe features around black holes, stuff like that, right?
Yeah, so I joined a group recently who is one of the best in the world at this. They model black holes, the regions around black holes, the accretion disks, which I mentioned earlier, which is, this swirling gas and plasma around a black hole, and it's falling into the black hole. What sort of emissions can we expect to see from that? Excuse me. What sort of emissions can we here on Earth identify that as? You mentioned quasars in passing, Kev.
Yeah.
For the longest time, we didn't know what a quasar was. We had no idea. We named quasar because we thought it was a quasi-stellar object, which literally means nothing. The name doesn't mean anything, quasi-stellar object. It essentially just means it's not a star. We don't know what else it is. What it is it's gas falling onto a black hole, passing the event horizon, and in the process, you get these long magnetic fields like funnels that come off of the black hole in both directions. And they are, tiny little cylinders, if you will, and they accelerate gas along them at very high speeds. And what sort of emissions can we see from that? And the way to answer that question, Kev, is to set up an ideal system on a computer where you have a black hole and you have gas around it, and you put gas onto the black hole, and you form these jets, and you look to see, if I was out here at the Earth and the black hole was all the way over there in another galaxy, what is it that I can see? How can I know that thing's there? And can my model match what we observe? That's the question.
Absolutely. Speaking to you, it really is. It's so encouraging, so exciting as well, because a lot of the time on the show here, we tend to cover some of the more depressing aspects of life. But living in 2019, it's almost like there's a thirst. Most people I know are so into science. They so want to listen to this kind of stuff. And for me, that's really exciting, Brendan. And it must be even more exciting for somebody like yourself in that, or just about to embark on a career in that.
Yeah, Kev, I'll say this because I want to give the audience a sense of where I come from, okay?
Mm-hmm.
I got into science. I was very much the conspiracy theory guy, actually, as a teen and into like before I turned 20, maybe 18. I was the guy who was, going on Infowars.com. I don't even know if that exists anymore. I think Alex Jones just got put up, shoved off the internet. I was the guy who was watching all the documentaries. I was the guy who was, being like, whoa, watching Ancient Aliens and trying to figure out if the pyramids are some master scheme by some extraterrestrial intelligence. I was the guy who was like, oh, the Bloomberg, the what's that? What the Bilderberg meeting is taking place. That was me. I was that person. And at the same time, Kev, I was not using logic the way that maybe I should have been. And part of that, Kev, comes from the fact that I was skeptical about authority in general. I was like, no, the federal government's lying to us. They're trying to take all our money. They're trying to steal from us. But the truth is that government is completely ineffective, completely inefficient, and the people running your government are probably pretty stupid. But what happens is that then people start to extrapolate that fact amongst all of the things the government does. But the fact is that at NASA or at the European Space Agency, these people are just ordinary people. They probably go home. They might even watch some conspiracy videos. They might do that. They just go home. They watch TV. They go for a jog. They drink a beer. They do whatever. They're not plotting against you. They're just trying to do something they love, the same way that anyone else is trying to do something they love. And frankly, it can be disheartening sometimes when you're working on something for a long time, just have people say that they don't believe you because you're affiliated with NASA, who is affiliated with government, who is affiliated with incompetent people.
Mm-hmm. Absolutely brilliant. And that goes a long way to almost what I was saying, where I started off. Sounds like we're very much on the same page, on the same frequency, Brendan. I'm still there in some respects. I do still go to Infowars. But like you were saying there, over time, I've started to realise that there is a more logical Occam's razor answer to a lot of the things going on. And I think we mentioned before the show that, it is right to question everything. that authority tells us, but not to the point where we don't believe anything coming from people in positions of authority, i.e. anything NASA says to us, we must automatically discount because we don't believe them. Yes, question it, but we mustn't throw the baby out with the bathwater, so to speak.
Yeah, I agree. This is all I ask from people who have alternative theories about anything. The solution is very simple. All you got to do is see if your theory can make a prediction. If your theory can't make a prediction, then it's not a theory, okay? And you should probably throw it out. But if it can make a prediction, test the prediction. Find out if it's right. If it's not right, then maybe your theory either needs to be tweaked or it's wrong in general. That's all I ask. I don't tell people to abandon their ideas and they're stupid and they don't know what's going on. All I say is this: test it. If you're a flat earther, come up with the money. Email the Flat Earth Society. I'm sure they're getting a lot of money.
I will help with the GoFundMe just to get this argument off the table.
Yeah, I'm sure there's tons of people who support. Go on Flat Earth Society website, follow them on social media, whatever. Pull together money, send a hot air balloon up into the upper atmosphere, see if you can see a curvature. Just see. If you can't, maybe the Earth is flat. Maybe, or maybe you haven't gone high enough. Okay? But either way, test the prediction and do it right and come to a logical conclusion. That's all I want, because that's what scientists do, and that's how science progresses. The reason that you can't sort of falsify the flat Earth theory is because they're not making a prediction that they will test. It's easy to, I could say that there's aliens over Los Angeles. I know that there's aliens over Los Angeles. They're floating over Los Angeles right now. But if I never go to Los Angeles, and I get out my binoculars and I start looking and making sure there's no aliens, then I can forever hold that idea in my head. I need to make a prediction. My prediction is that there's aliens over Los Angeles, and I need to drive there to test it, because that's the only way that you can verify whether or not your idea is right or incorrect.
Absolutely brilliant. Now, we've only got about 7 or so minutes left, and I often talk about CERN. I love CERN. I love the whole topic of CERN. And we hear about CERN, their own scientists talking about when they do these collisions, they momentarily create portals to other dimensions, okay? Now, time to time, I've described that, probably wrongly, as being, well, I know it's wrong, as micro black holes that are creating these in the lab. Now, it's not black holes per se, is it? And what's your take on CERN?
Now, this is interesting because CERN could, if our understanding of the standard model of particle physics is correct, CERN could produce a microscopic black hole. But the decay time of that black hole is on the order of 10 to the negative 27 seconds. In other words, a zero, with a decimal rather, with 27 zeros and a 1.
So it's not
seconds.
Even a blink of an eye.
Such a small fraction of time, that could not possibly wreak havoc on any of our systems. And they would be able to detect whether or not they had produced one of these microscopic black holes. I mean, if you're interested, people, you can go on the CERN website and they talk about some of the stuff on there. The update to CERN is very interesting. I'm amazed, actually, that they're updating it to the magnitude that they are.
It's huge. The future.
Yeah. Now, there was a second part to your question, Kev. What was it?
It was basically the production of black holes, and this fact, they say it's portals to other dimensions. What do you make of that?
Yeah, well, it's not
really more the mathematics involved.
Well, what my understanding of this sort of like, can we find another dimension using CERN, is more or less something like this. There are certain particle physics models that predict the existence of more than our 3 dimensions of space.
Yeah.
Okay. And the way to test, since we've been talking about testing, the way to test that model is that the model makes predictions about certain particles that should exist. And the only way to tap into these particles, if you will, and if a particle physicist is listening, they're probably like, oh no, I could do this so much better. If the only way to tap into those sort of extra dimensions is through high energy collisions. And so what we do, Kev, is if we can smash two protons together or two subatomic particles together, and we see that we have produced a very particular type of particle, then maybe, just maybe, if the prediction meets, or if the experiment meets the prediction, and the prediction says that, oh, the CERN has tapped into the fifth spatial dimension, and therefore the muon should be produced, and we detected a muon, therefore we must have tapped into the fifth spatial dimension. You know, string theory is very popular on this, M theory type stuff, where they predict, 10 or 11, depending on which theory you abide by.
13 they're up to now. Probably give it another couple of weeks. It'll be 14 and 15.
Yeah. Well, it's all different models. They predict different number of dimensions of space. And then in each dimension of space, you could produce a different type of particle, et cetera, et cetera. And a lot of it, I will tell you, outside of the particle physics community, very few people understand it. It is heavy stuff.
Yeah, quantum physics is heavy enough without going into the whole string and membrane theory, but we're almost out of time. And I know we were going to talk about renewable energy in Scotland. I know you had a pile more notes written down there, so hopefully I shamelessly get you back on in the near future to continue this conversation. But your final thoughts for the audience, and again, just let them know where they can find your podcast and when they can hear it, and anything you want to say before we leave tonight.
Yeah, well, Kev, I thank you for having me. This was a very enjoyable conversation. It's a whole different feeling to be the person being interviewed as opposed to the person doing the interviewing. And it might take just as much work. I thought it would be, a little bit more laid back, but I think you really have to make sure that when you come at this, you're doing it correctly so that you don't look like a fool. Because if you look like a fool, then people are going to say, wait, this guy doesn't know anything.
Well,
and so
that hasn't come across tonight, Ben.
Definitely not.
Yeah, and so I thank you both for having me. Anyone out there listening, I thank you for listening. I hope you can check out my podcast. It's called The State of the Universe. We have some, because I'm in the world of academia, because I'm in the astrophysics community, this year we will have some Nobel laureates on my show. I'm not going to release names yet, but I'm telling you that you will recognize these people. I hope that you come. Next week we have Julia Young, who is an expert on Mexican immigration. We're going to be talking about why Mexican immigration happens if you live in the United States. Is the wall going to deter it? Why does it happen? How can we prevent it? That sort of thing. And we just try to do very much what you do, Kev. We try to cover topics that people are interested in hearing about. And one of the things that I try to do is I try to do what you try to do and talk to the experts, the people who know their subject better than anyone else. And so I hope that anyone who's listening to this can come on over to The State of the Universe. You can find it on YouTube, Apple Podcasts, Stitcher, Google Play, Spotify, anywhere that podcasts are found. My website is thestateoftheuniverse.com and check it out.
And remember the name, ladies and gentlemen, because I think we'll be hearing this more in the future. Brendan Drachler. What an amazing show. What an amazing guy. What an amazing guest. And all of you out there are equally amazing. Remember, keep your minds open, but don't let your brains fall out. And until next time, wherever you are, make it TFR.
And didn't touch that dial.